All right, so let's take a look at superposition and interference. So superposition is going to be looking at two waves and seeing what happens when we combine them. So in this example, we have one pulse over here and we have a second one over here. What happens when we combine the two? We say that we superpose them and we apply what's called the superposition principle that tells us that we can simply just add the two waves together. So I can take this plus this, and that is going to give me this superposition of the two waves. So we're doing a simple addition of the two. Okay. Um, so a couple of things can happen in this scenario. Well, a lot more than a couple of things, but there's two particular cases that we may be interested in. We may have what we call constructive interference when our pulses are going to combine to get to give us a larger pulse. If we get the opposite, so we may have one pulse up and one pulse down, we're going to end up with destructive interference, essentially because we're adding two things that are in opposite directions and they may cancel out. We're going to talk more about that and its applications in a minute, but let's take a look at a visual representation. Over here we have two waves traveling in opposite directions. To the left, we have two waves that are, essentially have, they're up. And so when we add them together, we end up with a larger pulse. And then they continue moving. So this one was traveling to the right, continues, and then this one was traveling to the left, and it's going to continue. For destructive interference, you can see that as they cross, and you can see that in this case, they have the same amplitude but opposite directions. So one up, one down. And so you can see that as they meet over here, everything is gone. So we're dealing with destructive interference in that case. So in general, if we're looking at two waves that we're going to add together, not just a pulse, you can see that this would be a representation of each of the waves. And for constructive interference, you can see that we're going to have, so we're going to maintain everything the same, but the amplitude is going to increase. If we shift everything, you can see that here we have one wavelength going from, this point to this point. All right, and here you can see that we say that these two waves are in phase, they match, right? So peak here, max and max are gonna match. But if I shift everything over, all right, so that now I have a maximum that's going to match a minimum and vice versa. When I add those two together, if they have exactly the same amplitudes, they're going to cancel out. So we say that these are out of phase and these are in phase. When I add two waves in phase, if they have the same amplitude, we're going to double the amplitude. If they are out of phase, it's going to cancel out. So this is interesting because that means that, for example, if you're trying to build noise canceling headphones, what you need to do is essentially get the signal for the sound that you're trying to cancel, and then you can add up another one just out of phase to cancel that noise. All right. What happens if you add two waves together, but now they're not going to have the same frequency, they're going to have slightly different frequencies. Well, now we're going to have something that is going to be a little bit more complex. All right, so you can see that we have two signals, so one in blue, one in red. We're going to add the two together, and you can see that we have here in two of the same amplitudes, but you can see that, so here this is shown as a function of time, and you can see that we have different periods, which means that we have different frequencies. And when we add these two together, so you would essentially add the signal. So this plus this, I would end up here. This here, we have the two maxima that match, so we're gonna get a maximum over here. And we end up with this interesting pattern. So we have essentially two waves in one, because we have kind of an envelope layer here that is described by a wave, and then we have one within, which with a larger frequency. Um, and what we're creating here is beats. So that's an effect that you can use to tune a musical instrument, for example. So usually, if you're tuning a guitar, for example, you could have a tuning fork that gives you exactly the frequency that you're trying to get. Then you can play your note with whatever instrument that you're using. So if the two frequencies match, then you're going to essentially get a nice sound that's going to sound essentially a little bit louder. If it's not tuned correctly, you're gonna hear those beats. So I'm gonna add some videos so that you can hear the difference in the vibration that you'll hear with the beats. All right. So this is wave interference. And in the next video, we're going to see how we can use this to create what we call standing waves. And standing waves are very important when you're building musical instruments, for example. All right, so stay tuned. Thank you. Bye.